breakthrough in biodiesel production, one that could change the way we think about renewable energy. We're going to look at how simple enzyme T1 lipase can make biodiesel production faster, more efficient, and more sustainable. This enzyme is the key to unlocking better fuel from waste oils. Are you ready? Let's get started. Alright, so first let's talk about what is biodiesel. Biodiesel is a renewable, biodegradable fuel made from natural resources. Things like vegetable oils, animal fats, or even recycled cooking grease. In essence, it's an eco-friendly and cost-effective alternative to traditional fossil fuels like petroleum. So how do we make biodiesel from used palm oil? First, we filter out food particles and dry the oils, and then we convert it into fatty acid methyl esters, or biodiesel, and glycerol through a process called transesterification with methanol. The biodiesel and glycerol are separated through a method called settling, and then the biodiesel is washed and dried to remove any impurities. And it's a pretty standard process, but we can make it a lot better with the right enzyme. So there are two main ways to carry out transesterification. First, chemical, and second is enzyme method. So the first one, the chemical method, is fast because it's using catalysts like sodium hydroxide or sulfuric acid. It is highly efficient and widely used in industry, but it's also harsh on the environment. Enzymatic transesterification, however, uses lipase enzymes to catalyze the conversion of oil into biodiesel. While it's lower and more expensive, it's also much more eco-friendly and can work with low quality or waste oils. For us, enzymatic transesterification is the better choice when it comes to sustainability. And this is where our T1 lipase comes into play. T1 lipase comes from a thermophilic bacterium called Biodiesel species strain T1, and it is especially special because it is thermostable, meaning that it can stay active at a high temperature. This is great for biodiesel production because it helps to speed things up, reduce contamination, and even better, we can immobilize the enzyme on solid support like beads, which makes it more stable, resistant to methanol, and reusable. This could be a game changer for industrial biodiesel production. Alright, now let's take a look at the challenge that we need to address with lipase catalyzed transesterification. So the problem is methanol. While methanol is essential for biodiesel production, it is also toxic to lipases, where high concentrations of methanol can disrupt the enzyme structure, causing it to lose its activity. And this reduces the biodiesel yield and increased costs. And since enzymes are expensive and need to be replaced often, so we make lipase more stable in the presence of methanol through a process called protein engineering. So let's take a look how we can make T1 lipase become more stable and resistant in methanol. So we use a technique called consensus sequence design, which means that we look at the lipases that are naturally good at working in methanol-rich environments such as these. And we borrow the best part from their genetic sequences and combine these traits with the T1 lipase. And we can create an enzyme that's even more efficient and stable in methanol. So now how exactly the consensus design works? So we start by analyzing the sequences of lipases that are methanol tolerant. We look at where the most stable amino acids are, like here, and then we combine these features into our T1 lipase. And to analyze, we analyze the enzyme 3D structure to see how the changes will affect its stability. And once we identify its best mutation sites, we apply them through site-directed mutagenesis, a method that precisely alters the T1 lipase gene. And now we have the modified gene. We then transform it into bacteria, which produce the engineered lipase for us through overlap extension PCR and sequencing. Now we test the new enzyme T1 lipase with the wild type enzyme and the commercial lipases. The results were exciting. Our modified enzyme stayed active in methanol longer, as you can see here, and worked more efficiently in converting palm oil into biodiesel. This is exactly what we needed to improve and achieve higher biodiesel yields. Now let's take a look at the prototype, how we make it. So the modified T1 lipase is embedded in silica beads, which can withstand high temperature without affecting the enzyme activity. These beads are then used in biodiesel production, converting used palm oil into biodiesel. As you can see in the image here, where the yellow turns dark brown biodiesel. It's great thing that these beads they can be reused multiple times, reducing the need for fresh enzymes and cutting costs as well. Now when it comes to storing the enzyme beads, there are two options where for the long-term storage we kept it at dry temperature, and for short-term they can be kept in trace hydrochloric acid buffer solution at lower temperatures. This keeps the enzyme active and ready to be used whenever needed, ensuring maximum efficiency. So why did we choose consensus sequence design over the other methods like directed evolution? The answer is simple. Because consensus sequence design is much more straightforward and reliable. Because we know exactly what to work with, and there are also a lot of database to support the methanol tolerant lipase sequences. Where directed evolution, on the other hand, might give us random mutations that could be hard to manage and control. And the consensus sequence design let us take more controlled approach. Now let's talk about how we're going to bring this technology to the market. Our customer are biodiesel producers, both large and also small. So in our customer segments, T1 lipase is designed for biodiesel producers such as Geno, Matica in the USA, and EcoOils in Malaysia. These companies can leverage the enzyme to improve its sustainability, reduce the cost, and meet increasing global demand for eco-friendly fuels. Secondly is customer relationship, where we focus on providing exceptional technical support and collaborative partnerships, working closely with customers to tailor solutions that optimize their production processes and meet specific needs. And the channels that we use to connect with customers is through online platforms like LinkedIn and ResearchGate, where we publish research in scientific journals and present it in industry conferences to build credibility and expand our reach further. Now, what's our value proposition? In simple terms, it's about making biodiesel production more efficient, cost-effective, and sustainable. Our T1 lipase offers enhanced stability in methanol, allowing for faster reaction and also higher biodiesel yield. Plus, because the lipase is reusable, so the producer can save on enzyme costs and making the process more economical in the long run. And our revenue comes from direct sales, subscription package, and enzyme refills and support, as well as licensing options for custom formulations tailored to specific feedstock to drive both market expansion and customer loyalty together. And to make all this happen, we focus on key activities like protein engineering, enzyme production, and creating enzyme immobilization kits. And we also be testing on and refining the enzyme in real-world biodiesel production systems to ensure everything meets safety and environmental standards. To support this, we need a skilled team, talented team of biotech experts, engineers, and also access to high-quality lab equipment. And not to forget materials like sodium alginate and calcium chloride, which is important to immobilize the enzyme. And we also rely on strong partnerships with biodiesel producers like Saudi Oils in Malaysia and Biocon Malaysia, and also university like UTM to help refine and scale up the technology. Our main cost structure come from R&Ds for stabilizing T1 lipase, enzyme immobilization for reuse, and also bioreactor reaction operation with palm oil waste. And other significant expenses include methanol procurement and fuel-grade biodiesel blending. So as we can see here, the key results that are most expensive are the biotech R&D infrastructure, where it costs us 500,000 ringgit per year. And then we have feedstock for palm oil waste that costs 1,200 ringgit per ton, and the immobilized T1 lipase production that costs us around 200,000 ringgit per setup, and lastly the skilled biotech talent that we will be using, which also costs us 250,000 ringgit per year. So in conclusion, what we're working on isn't just about making better biodiesel, but it's also about creating a more sustainable future. By improving T1 lipase and using it in biodiesel production, we're aiming to make the process more efficient and cost effective, and as well environmentally friendly. So thank you for your time, and I'm excited about what we can achieve together. So that's all. Thank you for listening.